Okay, welcome back to part 2 of Biomechanics. We're going to extend what we looked at last time and then start to apply a little bit of our understanding around things like balance, stability, and mobility, and how we can use those things to our advantage. So we're going to look at Newton's laws of motion. You may remember some of these from school science. We touched on what a force was last time, and I guess the key thing with a force is that forces are what causes position change in masses. So a mass could be yourself or a segment or like a implement that you are throwing. We'll look at how the body uses levers to help move and shift things. Equilibrium, so that's when we're going to look at the stability and balance stuff, and then how center of gravity affects stability and balance, our base of support, or what a base of support means, and line of gravity. So Newton's first law, Newton was a scientist that loved understanding forces and things like gravity and how those forces interact with us in our everyday life. And his first law is the law of inertia, which states that every body continues in its state of rest or of uniform motion in a straight line unless compelled to change that state by forces impressed on it. So if we try and put that simply, an object will move or stay at rest until another force is applied to that object to change its state. So if you think about like an object sitting on your kitchen bench that isn't moving, it will stay in that position because all forces around it are currently equal. So gravity will be pulling down on it, but the table that it's sitting on will be pushing forces up into it to keep it still. That will stay in that position until another force is applied. So it could be a force like you coming along and picking that object up. You then have to resist the inertia in that object, apply force through your arm to lift it up, and changes the state of position or state of motion. So law of inertia is used to describe an object's resistance to motion. So I've got a picture here of a sumo wrestler, lots of mass, plus the acceleration of gravity pulling down on a big mass means that a sumo wrestler is hard to move, and they are big in terms of their mass, so that they are hard to move. The rules of sumo wrestling is if you can push your opponent out of the ring, then you'll be successful. We have a 200 kilogram sumo wrestler pushing against a 60 kilo sumo wrestler. Which one has more inertia? Which one has a greater chance of being successful? And inertia is directly related to an object's mass, or the amount of matter that makes up that object, and that's measured in kilograms. Okay, so Newton's second law is the law of acceleration, and it states that the change of motion, so motion meaning the change of movement in an object, is proportional to the amount of force that you put on it. So the more force you apply, the more change of motion that you're going to have. And this change of motion is going to be made in the direction of a straight line in which that force is applied. So the equation for the second law, Newton's second law, is force is equal to the amount of mass that you have times the amount of acceleration that is applied. So if we think about a discus thrower, generally if you think about this, what they look like, they're often quite big. So they have a lot of mass, which is great because that means more mass is potentially more force production, but you also need to be able to move fast. So if you think about what a discus thrower looks like when they move, they use angular momentum to generate that acceleration. So big mass, fast movements, big force, big throw. If you think about contact sports like rugby, rugby players are generally quite big, especially when they're in a position where high contact is beneficial. So high force is needed. So you need to find a balance between having a good amount of mass and also being able to apply a good amount of acceleration. If you are too heavy, then what will start to happen is that the acceleration component will come down. So there's a bit of a balance between mass and acceleration in terms of force production. And Newton's third law of motion is the law of action and reaction. To every action there is always an opposite and equal reaction. So if you apply a force into something, there will be an equal but opposite force applied. This law illustrates that forces never act by themselves, but they're always in pairs. If we consider jumping on a trampoline, when your mass accelerates down because of gravity, the trampoline elastic energy within it is going to stretch, and when it stretches enough and generates enough force that matches that of your mass and gravity, what's going to happen is it's going to actually apply more force and oppose what you've just created. So types of forces, we can split it into contact and non-contact. The forces that exist in nature and affect the way we move as humans can be classified in a number of ways, but the most common classification is to describe forces as contact or non-contact. So contact forces involve the actions of pushing or pulling exerted by one object with another, whereas non-contact forces are forces that are exerted by objects that are not in direct contact with another and may actually be separated by quite a lot of distance. So contact is when there's some pushing and pulling directly with two objects, whereas non-contact is when a force is applied but there actually might be some distance between those two objects. So in the investigation of how humans move, the most familiar and probably important non-contact force is gravity. The force of gravity causes an object to accelerate towards the Earth at a rate of 9.81 meters per second. So the -2 means that it's an accelerating force, so it's increasing. The Earth itself, when you're on the surface, provides a force that is equal to your weight. So that's why when you're on the ground, you stop. So your muscles are creating force to keep you upright. If your muscles relaxed, then the amount of force that gravity is applying to your mass or your weight, you would actually collapse. So the equation to work out your weight is actually a vector quantity, and it's actually your mass times acceleration, which is measured in newtons. So when we say I need to weigh myself, or what's my weight, the accurate way to describe it would be in newtons, not actually in kilograms. That's describing mass. So in Moodle there's a link to the Trail Guide Biomechanics gravity video, so just pause this and check that out. So there's different types of contact forces. So these are quite common. Ground reaction forces, you'll work with athletes that have to produce lots of ground reaction forces. To lift something off the ground, you're going to have to apply force into the ground to then pass that into like an Olympic bar over your head. If you need to propel yourself over a bar like you would in high jump, you're going to have to apply high ground contact forces to be able to generate the amount of power you need to get over the bar. So ground reaction forces are the reaction forces provided by a surface upon which one is moving. So maybe it's the tar seal that you run on. Components of ground reaction forces can be measured in the vertical, anterior, posterior, and medial lateral directions. So when we run, we're actually generating a lot of vertical and forward and back motion, but there'll also be a bit of medial lateral directions. And if you're measuring this kinetically, you'll need some special devices that measure ground reaction forces, so force plates. Joint reaction forces, when joint reaction force analysis is conducted, the segment is separated at the joints. So we're looking at the forces created around a joint. So we're looking at a joint specific force production. So you might look at a kinematic analysis of, say, running and go, the hip is really important because there's a whole lot of hip extension during the contact phase of the ground, You could look at how much force is generated in the ground, but you might want to know, well, which joints are creating the most amount of force. It could be ankle, knee, or hip. So we can look at things like EMG or muscle activation measurement strategies to look at what muscles are contributing to force production compared to other ones that are part of that kinematic analysis. So that would be your kinematic analysis. What does it look like in terms of running? Your kinetic analysis would be, okay, so what are the actual forces that are being applied at each specific joint? Friction you'll know of. It's a force that acts parallel to the interface of two surfaces that are in contact during motion. A slippery surface has low friction. A really like sticky or rough surfaces have high friction. Friction creates heat. So part of even like massaging somebody, increasing blood flow and brings heat, but also you're creating friction between tissues. Other forces are resistance, fluid resistance, and in many activities human motion is affected by fluid and the fluid in which these activities are performed. So like swimming through water creates more resistance than going through air, and both air or both gas and water are considered liquids in this kind of context. And the two properties of fluid that are most affected, or that most affect objects as they pass through it, the fluid's density, so how much matter is squashed into a space. So if you've got a lot of matter in a small space, then you're high density, and then viscosity is to do with fluid's resistance to move. So just to recap, density is defined as mass per unit of volume or space, and viscosity is a measure of a fluid's resistance to flow. So if you try and suck honey through a straw compared to sucking water through a straw, the honey is going to be higher in viscosity. And I think that there's probably a correlation between density and viscosity. If you've got high dense fluid, then the viscosity is going to go up too. Some more types of forces: contact forces, inertial forces. These are forces generated by a more distal segment through muscle contraction. So remember, inertia is to do with resistance to move. So what happens here is exerting a force on a more proximal segment, not due to muscle action, is considered an inertial force. So it's to do with once a segment has started to move. So here is a better example to help make this a bit more simple. It's the swing face during running. So when you lift your hip into flexion, there is going to be some inertial force created at the knee joint, almost like a pendulum, where the foot will swing forward. And a lot of that inertial force is not actually coming from quadricep contraction. It's coming from swinging through like a pendulum. So the force in terms of muscles is actually coming from hip flexors, rec fem, and like iliopsoas, and then the knee extension. Some of that, or a lot of that, will be inertial force. Muscle force, so that's force generated by our muscles. Remembering that muscles can only generate a pulling force, so you can measure how much force a muscle produces. So there's actually different kinds of equipment where you can measure the amount of force that a muscle can generate. You can also look at muscle activation too through electrical stimulation. Elastic force is stored and released force from material with elastic properties that are put under stretch. So think about the elastic properties of our muscle tissue, or the musculotendinous unit. So we've got the endomysium, perimysium, and epimysium, those different layers of connective tissue. They provide some elastic potential energy, and then condensed at the tendons and ligaments, they're also connective tissue structures that will provide elastic force. Okay, so we're going to look at levers. Levers are structured in three ways, and this is the key concept to understand, and then we're going to actually watch some videos on the 3 different levers. You've got a point of axis or a point of rotation. You've got an area where effort is being applied, and then you've got another area where resistance is being applied. If the effort is great enough, the resistance will move. If the resistance is greater than the effort, then the effort will be negated or less. So these 3 things are common in levers. So the videos are quite good at explaining and visualizing what levers look like and applying it to real life. So pause the video and check out the intro to levers. First class levers are really good for force amplification. So in terms of exam questions, being able to explain when each type of lever within the body, what its outcomes are. So producing a lot of force for first class levers doesn't allow for a lot of range of motion, and it doesn't allow for a lot of speed. So an example in the body is the joints of your cervical spine are an example of first class levers. Check out the video on first class levers, really good visual explanation. Second class levers, also really good for force amplification, limited range of motion, limited speed. They are like a wheelbarrow where the pivot is at this end, and the force happens at this end, and the resistance moves in the middle. So plantar flexing your toes, like doing a plantar flexion, heel raise is a good example of a second class lever within the body. The calves are up the top, providing the effort. Your body is the resistance that it's moving, and then the pivot is happening at the end, like just like a wheelbarrow where the pivot is at the wheel. Same thing. Check out the video on second class levers, really good visual and some good application to real life. And the last one is third class levers. So they're not so much about force amplification, but range of motion and speed. And if you think about our appendages and our limbs, our arms and legs, they are designed to allow us to move well and to do it quickly. So most of the joints within the body are examples of third class levers. So check out before we do that, I guess other areas of interest, if you think about biarticular muscles. So here we've got an example of the hamstrings crossing the knee joint, but then also the gastroc crossing the knee joint here. So collectively, you've got third class levers supporting each other to create knee flexion in here. Obviously your hamstrings create most of the knee flexion, and the gastroc is more responsible for plantar flexion, but the gastroc contributes and assists. So if you're having to generate a lot of force in knee flexion, then you've got this double leverage of third class levers to contribute to force production. Check out the video on third class levers. Again, it's really good visuals and explain with examples in real life as to how these work. Okay, the next part is equilibrium. Equal meaning the same, and we're going to look at stability and balance. A state of equilibrium exists when the acceleration of a system is zero. So a system could be an object or a body. The concept of stability is very closely related to equilibrium. Stability may be defined in much the same way, that is, as the resistance to both linear and angular acceleration. So being stable means that you're resistant to outside forces coming in and changing your position. So if you think about sports where being stable is important, it's about being resistant to forces. But there's also sports where being unstable is important, where you want to be able to create a lot of movement with a limited amount of force. So if you think about gymnastics, where they need to lose stability all the time in order to tumble and fall and create those kind of rotational movements. So there's places for stability and instability. The ability of an individual to assume and maintain a stable position is referred to as balance. Even in a stable or balanced position, an individual may be subject to external forces. So sometimes forces are just too big to be able to withstand. Walking is a good example of losing stability on purpose, and then you regather your stability in terms of putting a leg out to maintain balance. If you didn't put the leg out, then you would fall over. So we've got these different ways of explaining stability. So stable equilibrium is if an object is displaced. So remember last week or last time we talked about displacement. If an object is displaced as a result of work done by a force and returns to its original position, then it's said to be in a state of equilibrium. So the example here is if this block, the blue block, was lifted up and then let go early enough, it would return back to its normal position. So it's in a stable equilibrium. This lady lying supine on her back is in a pretty stable position. If you'd have to apply a lot of force to change her position. Unstable, so here's an example of an object being displaced as a result of work being done by a force that then increases its displacement or moves further away. So it's said to be in a state of unstable equilibrium. So if you imagine this triangle on its tip, it wouldn't take a lot of force before it moves into a different position to where it started, or it was displaced somewhere. So if you look at this diver, he's standing on the edge of a platform. His base of support is tiny, so it wouldn't take a lot of force for him to lean over, and then as a result of that instability, his displacement would change, or his position would change. And then a neutral stability is if an object is displaced as a result of some force being applied or some work being done, and it does not return to its original position, but remains in the new position. It's said to be in a state of neutral equilibrium. So if you were to roll a ball across a table, it doesn't return back to its normal position. It would just roll and then it would stop. Okay, so center of gravity is a hypothetical point around which the force of gravity appears to act. So within an object or within a person, it's the point at which the combined mass, so the matter that makes up the person, the combined mass of the body appears to become concentrated. Because it's a hypothetical point, the center of gravity need not lie within the physical bounds of an object or a person, which means that it could lie outside of that person's physical mass. Base of support refers to the area beneath an object or person that includes every point of contact that the object or person makes with a supporting surface, so it's contact with the ground. These points of contact may be body parts like your feet or your hands, or they may include things like crutches or the chair or what a person is sitting in. So if you think about adjusting your base of support, what that does to how stable you are in position. But also think about if you start shifting your center of gravity around your base of support, what that might look like in terms of your stability. And then the line of gravity is an imaginary vertical line which passes from your center of gravity, where all the mass seems to be condensed, of the object, and the ground. It's also known as the line of action of the force of gravity. So the line in which gravity applies most of its force and has the biggest interaction with the object in question. So we're going to now apply those three concepts to some, I guess, human movement ideas or rules. So the lower a body's center of gravity, the greater its stability. So the lower you are, the lower your center of gravity is, the more stable you're going to be. So if you were to be pushed over by somebody, if you're standing up really, really tall compared to if you were crouching down really, really low, having a higher center of gravity is going to be less stable or easier, apply less force to push you over compared to if you were down low. So you think about riding on a skateboard or a surfboard, increasing stability on that. A strategy for beginners is to crouch down. The next rule is to do with base of support. If widening the body's base of support in the direction of the line of force will generate greater stability. So what that's saying is if we increase our base of support in direction of where an external force is being applied, then we're going to increase stability. So I guess what this means in terms of this baseball thrower or throwing a baseball is that this person's got a really wide base of support in the direction the ball's being thrown. So they've produced a whole lot of stability, which also means a greater opportunity to generate big forces in a stable position to then transfer the force into the ball in the same direction. If his stance was sideways and then was going to throw, he actually doesn't have a lot of support forward and back because the center of gravity is going to move outside of that base of support. But left and right, there's actually a lot of stability. So throwing a ball, base of support is anterior posterior, whereas if you think about a person trying to sidestep or change direction, then their base of support is going to be medial lateral in terms of how you produce that force. But bigger base of support, bigger stability, a space where you can withstand or generate more force. Okay team, so this is sort of summarizing base of support and center of gravity. The wording is a little bit confusing, so we'll try and break it down. So to maximize how stable you are, a person's line of gravity needs to pass through their base of support, and that base of support, where that line passes through that base of support, needs to be at a location that will provide the largest potential for movement, range of motion, in the direction of wherever those external forces are coming from, or in the direction that you want to generate those forces. So line of gravity passing through the base of support in the direction and where either forces are being generated or being received. In general, a person with more mass, so a bigger person, will possess greater stability. So this is a bit of the sumo wrestler analogy before. This little chap is going to have to create, if we think about the force equals mass times acceleration, in order for this little chap to match the force output of this big chap, his mass doesn't change, so he's going to have to input greater acceleration to match the force of the big fella, to match his force production. The body's most stable arrangement is when the center of gravity of each of the weight-bearing section is centered over the base of support. So this person who is jumping to catch a ball is not in a stable position because their center of gravity is not over the base of support, which actually have no base of support. Or if his foot, that one foot is touching the ground, very small base of support, his line of gravity is outside of that base of support. In this example, that is a good thing because it's allowing this person to change position really, really quickly. If you want to change your position really quickly, reduce your base of support and move your center of gravity outside of it. So if you want to walk, first thing you do is lift a foot off the ground. You've reduced your base of support and you move your foot forward, so that now puts your center of gravity forward, which creates movement in the direction that you want to go. So in the past couple of slides, there was a lot about like direction that force is applied. What they're saying is if you change your base of support and move your center of gravity in the direction you want to go, then that's where the force is going to direct or be directed. The more friction between two surfaces and the body's a surface and the body's point of contact, so your base of support, the more stable the body will be. If you look at sports where stability is important, then quite often there is equipment to increase that friction. So in rugby players, soccer players, there are sprigs because the ground can be quite soft. And then basketball, netball, you've got rubber soles to create friction against wooden floors. Other sports like ice skating, you want to limit the amount of friction so that you can use the force generated to increase speed. Okay, so this slide just summarizes increasing stability. So if we have a large base of support and we bring our center of gravity down, that increases our stability. So if I think about the surfing example, beginners to surfing will have this really wide stance on the board, and they'll also be really, really low. It doesn't look that flash, but it increases their ability to stay on the board. To increase stability, you need to optimize the positioning of your center of gravity in relation to where the base of support is. So if your center of gravity is over the middle of your base of support, you're going to be more stable. As soon as you move that center of gravity outside of that base of support, you decrease stability. Sometimes that's a good thing, sometimes it's not. It depends on what you're trying to achieve. And lastly, greater friction between two surfaces will increase stability. You try and run on ice, it's not going to be very stable. Now, if we want to maximize mobility, so that means how we move, then we want to decrease our base of support. Like I said, when we start to walk, lift your foot off the ground, you've now got one point of contact. You want a high center of gravity, so moving your center of gravity away from the base of support and then outside of the base of support is going to help us increase our ability to move. Having a small mass is also going to increase our mobility and low friction between surfaces. So this is quite important when you look at different athletes in terms of like what are optimal techniques towards movement, but also even body compositions and how athletes are built. You know, the structure of an athlete is generally feeds into things like how well they need to move, how stable they need to be, and the types of forces that they need to produce. Okay, team, that's the end, part 2. Our references are the Trail Guide to Movement, Building a Body in Motion. This Biomechanics book is in our library and it's quite good if like reading wider on this kind of topic might help. And then some of the diagrams are taken from our Merriam textbook.